instead. So no, just about a strange idea that we had because we had some trouble to store all of the data. So we call it METFLIX because it's really about that. It's about streaming data and using everything that is done for the weather for the video world to what we can do to handle our database. Why is that? Because, I mean, you saw this presentation last time. You look at the amount of data that you have to fusion when you want to do forest fires. Then you have minute scale radar data. Then your phenomenon, you need to have every 10 seconds time step. Because you need this high resolution and you need this high frequency because you are high resolution. So you end up with gigantic files and billions of time steps. That's the kind of stuff that is not normally stored in NetCDF files because it will explode your memory, or you cannot handle it. So you can buy a bigger computer, or you can try to find another solution. So this is why we need a resync, because otherwise a simulation like that will be a petabyte of data. No, you cannot do anything about it, and now you even want to have those to train neural networks. So you want to do some deep on it. So that means you want to have a lot of data. And then now the CDS store is fantastic. It's a lot of grid files. I personally like a lot of grid files, but they're quite heavy for exploration and even for so that's way. Can we trade a little? But they are scientific data. So, but can we trade a little bit of accuracy against accessibility? It's what exactly they done in METFLIX. They spend billions of euros to have some encoders and decoders and files, even in your mobile phone. So you have a chip that can encode and have all this data, any kind of data, a stream. So it's no problem for METFLIX to stream something that will be 4,000 by 3,000 at 30 frames per second, high quality data, and to stream so many channels for the same point. It's like a climate data store, but multiplied by 1 billion, and with all the data there, and everyone can access it. So it's orders of magnitude more efficient than a climate data store, which is great, by the way. So basically, what we get from the data store is that. I mean, you get a grid file, and I just take that as an example. So that's the land cover, so the dew point temperature. So you end up, when you get from the data store, a big grid file, which is a collection of hourly data for months of stuff. And it's already 4 gigabytes. But when you pass it to, if you ever compress it, you say minus 20 dew point degree is white, and the other one is gray. You put the bit mask aside, you encode it into the metadata, you put all this information in the metadata, then you end up to having MP4. And thanks to METFLIX on GitHub, now you can use the engine instead of Grib or NetCDF, you put AVEnc. And you have that. The file is actually 300 megabytes instead of 48 gigabytes. And it takes you 10 seconds because it's all using FFmpeg that most people should know. This is at the base of even Netflix to encode. So you can get a point here. And so FFmpeg is very efficient as getting 1 year of data. So 10 seconds to extract a time series. 10 seconds to make a subset, 10 seconds to take 1 frame each 20 frames, so 1 frame per day, and it will be 10 seconds also to download and to send it to a friend. Problem is that you will lose some data, and you will lose some quality. But basically, that means that you have to control that. So the basic idea is to treat each of the slices as a frame, and then you normalize it. So and you keep it in the minimax and the geotags all in the container. So you always have metadata in the MP4 file. So you put all that X encoded into it. So an MP4 file will be like a NetCDF file and so on. So it's not a totally new idea, because some people try to do some spatial temporal data compression, but then it didn't. It was before the X-ray world, and so we did that. And then the team of Oscar Pellicer in Valencia did also some stuff that went just out. And but they were more, so they tried this kind of approach in a pure Python way. Our AVENC is pure C++, so it's just because we do C++. And now there's even better. This paper from 24th of October, found by my PhD student, which is actually much more clean than that whatever could be expected. But it's another encoding things. But those are very, very good and better. So, but just to give you an idea, because it's always something else to think, codec. So you have many codecs. AVC will be the codec that is typically everywhere on every box and so on. You have HAVC, which is a new one from the Fraunhofer Institute, and which is better and fast at decompression and fast at compression too. And you got now the codec from Google that are fully open source because they want everyone on their platform, on YouTube and so on. So it will be EV1 and VP9, but will need hardware encoders because it's very complex. But look at what they do. First thing that they make a discrete cosine transform, just like you do with some of the approach that you should do. Then they do average, then do motion vectors, then they segment, and then they quantize. All of these algorithms, they do like that. These things, if you even think about it, when you train your network, you could directly train them on the coefficients that have been found by the HAVC things, especially if you plug that into that. Just to make you an idea, I made this is a fire. This is a coupled fire atmosphere simulation encoded into a buffer. So the fire is here. So it makes some perturbation on the flow. That will be the U field of the V field or whatever on the ground. So it will be a 5 GB of pure float 32. So but and I tried different kind of compression with the different encoder and different settings. So what you see is like max, if I quantified on 8 bits at maximum compression ratio, so I will have a compression ratio of 10,000 compared to the other one, but then I end up having that, and the error spectrum will be about Gaussian. And basically, you always find this one, a few extremum, so that you lose, but then otherwise things. And these are the different kind of, so this is GRIB AEC and CZIP and CU. This is this is lossless. This will be the lossless compression that will be directly available in GRIB and so on. But this is the kind of compression ratio that for the same flow field that you get for the data. So you can go up to 2,200 compression ratio. And so this is the same. So this is what it looks for at very high compression ratio, and that's the error field-ish. So the error spectrum now. And just to give you an, that is 10 gigabytes in no 600 megabytes. Sorry, I think that's what you have on the if you scan the QR code. That's things. So that is Arom 1 year of Arom hourly. So it's all open source. It's here, and you get a pure Python version. And the thing that if you use the C++, then you have just a binary that is METFLIX, but it should not be called METFLIX anymore because there's some problems. But and then you have a unflix to extract GRIB out of the thing again. But then what we wrote now is this X-array driver, so you can directly open the MPEG-4 in X-array. It doesn't unpack it in memory, otherwise it will explode your memory. So it's a lazy opening. Then you have to make a slice, and it's like a ZAR thing. So and it's not tested much. But if you think about it, what this enables, it's they make they it enables as well, and that's what we do, it enables that a model that is running like MesoNH. Now there are streams, so you run the model, and you connect it with this. You connect the model, and you watch his temperature fields as like you will watch a channel of simulation running. So you can. It's actually every data you should not have data. You have data streams. And everything could be seen as streams going out of information going out of a model, like it would be like information streaming from the TV. And it's also a set of transform coefficients that you can use to train the model, and because they are so packed, there's probably some kind of information. The idea of having streaming information is something that we work as well with the guy up there, because they had to work on the representation of their radar data. It's not METFLIX, but it's the same kind of idea of streaming data. And not radar, but lightning. So it's a network that we have in Corsica of Dominique Lambert, but this kind of network generates a lot of data when there's lightning strikes, because a lightning could be as much as 1,000 points. And when you have a lot of lightnings, then you will have millions of points in less than an hour, or even more than that. So on one day, you can have billions of points. And you cannot have that as a big file at the end of the day, because then you will have a big CSV file with latitude, longitude. And so if you pack it and you stream it along, then in a way that is, then it could work. So if you open the file, I mean, it looks like that. So basically, we designed a streaming process where you can it's actually stream data from the sensors, but every minute I get an update on that. And we use H3 for geographic encoding, so we can merge most of the data at higher resolution. So this is how the data that is now 5 megabytes that would have been 10 gigabytes. And could be played, and so it makes us easier to know where the lightning was, and even going down to so that I don't know if it could go down, but all the information, despite the fact that it's very, very compressed, all the information is there to even up to the 3D scanning. So so there's obviously some compression artifacts, but you can squeeze data flow, and it's open source, so please test it. So thanks a lot.